Good. So I was asked, but how about multiple classes? And this we will discuss in a minute. But before we do, let's look a little more at the properties of what this loss function looks like. Yeah. So to fit our parameters or to train what we can do is say beta hat is the minimizer of this function, which I'm going to write once more. And I forgot some subscripts here, xi. Okay. And we can look at this negative log likelihood and ask, as a function of mu, what does it look like? And now we can distinguish two cases. We can first ask for the case y equals 0. So I'm using green for the y equals 0 case. In the y equals 0 case, we have 0 times the log of something, and 0 log 0 is here assumed to be 0. So what remains is the other term. For class 0, we have minus the logarithm of 1 minus mu. So 1 minus the logarithm of 1 minus mu. So 1 minus mu, the logarithm would look like so. But now we have minus that. So what we get is a slope of 1 here, and then something which increases faster than this slope of 1. So it is this term which I'm plotting here. So what that is in words, if the true class label is 0, and if our estimate mu is significantly larger than 0, then we incur a big loss or a huge loss. And here I can make the same argument for y equals 1. I have a slope of 1 here. I have a function which increases faster than, which increases exponentially. And So if the true class label is 1 and mu is significantly smaller than 1, then we incur big loss. All right, now this minimization problem here, unlike the standard least squares case, has no closed form solution. So we need to find this iteratively. We need iterative solvers to find beta hat. And possible choices are gradient descent or stochastic gradient descent. Or another typical choice is a Newton-Raphson solver. So a Newton-Raphson solver is one if you're given some parabola. You can estimate the gradient and you can estimate the curvature. And then if your surface is a parabola, then you're going to find the optimum in a single step. And here, our loss function is not a parabola, so we're not going to find it in a single step, but we can just pretend that it's a parabola locally. Yeah. So we pretend that this loss function is a parabola and then iterate. And if we pretend that it is a parabola and iterate, this gives an algorithm which is also known by a different name. So there's the parabola and there's iterate, and together this gives an algorithm which is also known as iteratively reweighted least squares. Or IRLS for short. Okay, and now talking about how machine learning keeps changing over time. When I first taught about logistic regression, I was warning of the degeneracy. So what if the data is linearly separable? So we have X, and we have our samples of class 0, and we have our samples of class 1. Now, if the data is perfectly linearly separable, then the steeper I make my sigmoid, the better. So I can make my parameter vector beta is going to become very, very large, and I'm going to obtain what is practically a step function. But I could get this step function, or I could get that step function, or I could get that step function. Right? It's as long as I choose a perfect step function, this is not determined by the data of which one I should choose. Now, which one would you choose? You know, probably, I guess you would choose one which is roughly in the middle, right? And roughly in the middle, this would also be known as the hard margin solution in the world of support vector machines. So the hard margin solution is equally far away from the observations on either side. And so a finding which was not yet around when I first thought about logistic regression is from 2018. So Soudry in 2018. Proves that GD, gradient descent, if you let it run forever and ever, it converges to the hard margin solution. And this is also an interesting finding in this context of double descent and so on. So this paper from 2018 was argued explicitly, and this is before the term double descent was really known. This paper already argued that sometimes it can make sense, even after you fit your training data perfectly, to keep training, and there is a chance that you might get better on the test set eventually, even though you already perfectly overfit your training data. Okay, so the bad news is iterative solvers are needed. The good news is that the problem is convex. But it's a weird kind of convex problem. So, you know, normally when we think convex problems, we think that, all right, we have a clearly defined optimum. Need not be parabolic. It can, you know, also that would be a convex function. But here, the loss surface looks more like so. So in this here, this is the space of beta, and here is the loss. And if my data is perfectly separable, there is an incentive, you know, to make here the estimate, posterior probability estimate, here should be really 0, and here it should be really 1 to very, very high accuracy. And this means that it's beneficial to make the step function, or to make the sigmoid steeper and steeper until it's a perfect step function. And it becomes a perfect step function only in the limit of infinitely large coefficients in your parameter vector beta. And so the loss keeps going down forever, but it doesn't go up on the other side. Yeah, so it is convex, but yeah, if you let it run forever, it will run forever. It will go further and further out your solution. Now, on the other hand, you know, if really this is how many training observations you have, yeah, like 4 examples of the one class and 5 examples of the other class, and our hard margin solution tells us that on the right-hand side of this threshold, the probability of observing class 1 is 100%, and to the left of this threshold, the probability of observing class 1 is 0%, that I wouldn't believe that, right? Because the training set is so small. So in this context also, it can make sense to regularize. So to say, all right, this was my loss as a function of beta, but I now add a regularizer. For example, a ridge regularizer, which says that I have a parabolic penalty that grows as my norm of my vector beta grows. And then if I add the two, well, I get a loss function with a clearly defined minimum. Yeah, so if I take this and add it to that, sorry for the multiplexing here, I will get a loss surface. So this is now loss plus regularizer, which has an optimum somewhere. And then this is the optimum solution I'm going to find. And let me use a different color for that. So this solution would then, okay, it should be symmetric ideally. Will look something like so. So it's going to be less extreme. And for such a small training set, I would believe this regularized solution much more. Yeah? It tells me the posterior probability here is pretty low, and then it's 20%, 50%, 80%, and 100%. I would believe this more than a crass step function. All good? All right. So now comes the extension to multiple classes. And this is called, it has many names. It is known, for example, as multi-class logistic regression. Or it is known as multinomial logistic regression. Again, the regression, we should put it in quotation marks and remember that it's actually classification that we're talking about. Or it is known as the softmax. Or it is known as a maximum entropy classifier. It's all the same thing. And now here previously, we had that some label yi was either 0 or 1. Here it's with multiple classes. It will be more convenient if we use a one-hot encoding. So here we're going to use labels yi, which are vectors. And these vectors are 0 except for one component. And what we have is that, so this index is for the training sample. It's my ith observation. And this index is for which of the classes or which of the coefficients we're looking at. And we're going to say this is 1 if yi has class k, and it's going to be 0 otherwise. All right, and now just as in the previous case, we again need a noise model. And this noise model is not the Bernoulli, but it has different names. One name is the Multinulli. And then there was a bit of a debate on the internet and on Wikipedia and so on. And now a new name is emerging, which is the categorical distribution, which is maybe a bit easier. Yeah, so this is what it describes is one experiment with k different nominal outcomes. So I'm not saying throw a dice, because when we throw a dice, we normally get a number 1, 2, 3, 4, 5, 6. And here there's no ordering. In some games, you have a dice where I don't know, on one side there's a parrot, on the other side there is a diamond, and so on. That could be an appropriate model, yeah? So for tossing this kind of dice. Okay, so we have one experiment with k possible outcomes, and these possible outcomes have distinct probabilities. The probability for each of these classes must not be smaller than 0, and it must not be larger than 1. And altogether, they must sum up to 1. And for this logistic regression, we would now say that the probability of some random variable y at some feature x follows a categorical distribution with this parameter vector. Yeah, so it's really an extension of the Bernoulli that we looked at earlier. All right, and now we're going to use sigmoids once again. And now the sigmoid we're going to use, it looks a little bit different, but it's the very same in nature that we had before. All right. Now, this summation constraint here, that eliminates 1 degree of freedom. And for the 2-class case, we had that e to the b transpose x divided by e to the b transpose x plus 1. And here this looks a little bit different, but we can get them to match for, here this was the 2-class case, for a suitable choice of beta here. So in particular, this for the 2-class case, I could write as follows. I could say that this is, for example, e to the b transpose 1 x divided by so this is specialized here to 2 classes. And then I can divide by the numerator here. Then we get 1 divided by 1 plus e to the b2 transpose minus b1 transpose x. And here we had that this is the same as right, and now we see this relation here So this will be identical if I say that minus beta is the same as beta 2 minus beta 1. Or beta should be beta 1 minus beta 2. Yeah, so I have this extra degree of freedom from which the normalization removes. And this extra degree of freedom allows me to choose beta 1 and beta 2, whatever, so that it results in that value here. I don't know if that was clear. So what we do here is remove 1 degree of freedom, and that corresponded to the normalization constraint that we had here. All right, but so what does this look like? And now I'm going to be graphically challenged, but I will try. This is experimental, okay? Never a good idea. So oh, this is a bad start. The triangles are meant to be identical. Let me try again. All right. Okay, I hope your spatial perception kicks in. This is X. And now I have 3 classes. I have here class 1, class 2, and here class 3. And now we can have different examples. Maybe we have mainly examples from class 1 here, and then maybe we have intermediate some examples from class 2, and perhaps we have finally some examples from class 3. Oh, sorry, that was on the wrong axis. Here, class 3. And we are now looking for functions. We're now looking for an estimate that lives in this simplex. So here we have the simplex defined by the 3 classes. And we are now going to find this posterior. Here where I have mainly class 1, it's going to be around about here. Where I have mainly class 2, it's going to be around about there. And here it's going to be around about here. And so now I have this function living in this space. This is my posterior. This here is the probability of y given x. And I'm going to draw a different picture for the same truth. we had found for each of the classes one set of parameters. And let's say this here is beta 1 transpose X. And maybe this here would be beta 2 transpose X. And yellow for the third class. This would beta 3 transpose X. And what we have is that they can if we look at this, it reminds us of a Boltzmann distribution or a Gibbs distribution. Maybe the analogy becomes more clear if I say I have e to the minus, I have some inverse temperature, the energy of some state, let's say the kth state, and then I have the partition function. So this now goes over all states. This would be the energy of the kth state. These are the energies of all the other states. The denominator you know as the partition function. And what we get out here altogether is the Boltzmann or the Gibbs distribution. And what this Gibbs distribution does, if you have a system with a couple of different energy levels, okay, it's pretty arbitrary here. Okay, maybe I'm using equispaced ones. If you have a system with a couple of energy levels, of course, at zero temperature, you're only going to occupy the lowest energy state. However, if you say that I'm looking for a system, and let's say we have an absolute zero here in the energy, but if you say that I'm fixing the expected energy, perhaps the energy that I observe in my ensemble is such, I'm now looking over a distribution over my states, which has this average energy, but which maximizes entropy. And so you can write this as a Lagrange optimization problem. I am looking for a distribution, and you need two Lagrange multipliers, one for normalization, and the other one to give you this mean energy. And then you can say, I want to maximize my entropy subject to these two constraints. And then you find a distribution which looks like so. So you have exponential decay towards higher energies. And here we're using the same thing. So I could now use two axes. I could say here energy goes downwards. Because here I have a minus, and in my formula up there, I have a plus. So low energy is good. Low energy now is up here. And if I now plug these into my formula, I'm going to get posterior probabilities which look like so. Okay, approximately. So I have these linear terms, and then I put them in this function so that I obtain, let's say, generalized sigmoids, which have the property that they always sum up to 1, and they're bounded between 0 and 1, and they give me these posterior probabilities for my respective classes. So on this axis here, I plotted the probability of a given class at some location x. And at 0 temperature, we would normally choose the state with the lowest energy. Yeah, so this would amount to a step function where we say up to here we predict class 1, and here we predict exactly class 2, and there we predict exactly class 3. But at the moment we introduce some finite temperature, and in our case this temperature is estimated from the data using the maximum likelihood procedure. We get this distribution. We get the distribution over states, or here we get the distribution over different classes. So here, we don't use the argmax, but we are using the soft argmax. Yeah, so this thing here is a soft version of the argmax. And unfortunately, in machine learning, this is shortened as softmax. Yeah, so this is the famous softmax function from neural networks, but what it really does, it gives you a soft argmax. So, you know, max would be maximum posterior probability. Argmax would be which class gives you the maximum posterior probability. And what it does is the latter. Yeah, it's a softened version. It's an entropy softened version of the argmax. Okay, I'm not done explaining, but I'm running out of time. So I think we need to maybe look at that case a bit more in the exercises. Let me give a brief summary. So a logistic regression is a really practically useful method for discriminative classification. It motivates the cross-entropy loss that is being used in neural networks. And there is an extension to multiple classes which does encompass the two-class case as a special case. And this gives us the famous softmax from neural networks, and that's a misnomer. It should not be called softmax. It's really a soft argmax. Okay. Please prepare some questions which you can ask next time. We can go over some of these things again. Have a great time and see you on Thursday.